Okay, this is the problem. You are tasked to find for the EMFs, epsilon 1 or E1 and EMF 2 or E sub 2 in this circuit. Now I know this circuit looks intimidating at first sight because you have a lot of resistors, and the only given basically in this problem is you're being told that the current that goes in a junction A over here is 1 ampere, and the current that goes out of junction A is 2 amperes. Now I'm going to simplify this so that this won't be as complicated as it looks. It will look like this one. I simply rewrote everything. So R1, R2, your R3, R4, epsilon 1, R5, epsilon 2, and R6. Now, based from the given, this current represented by violet is 1 ampere. This yellow part is 2 ampere. And if you actually think about it, the current that passes through R2 and R1 are I1 and I2 respectively. However, you should note that your R2 and R1, along with the section of the conductor, is actually in series. Therefore, if you recall in our class, there is something constant in this circuit in R1, R2, and this part of the conductor's section. Now, also, if you think about it, there is another current that passes through R4, which we called I4, and through R3, resistor 3, which we will call I3. And the same also, current I5 for resistor 5 and I6 for resistor 6. However, as I've said, if you think about it, I1 and I2 will have 1 amps or 1 ampere. It is because resistor 1, resistor 2, and this section of the conductor is actually in series. Therefore, if 1 amp is given in this section over here, follow my cursor, that means to say that that same current is passing through resistor 1 and also through resistor 2 because they are basically connected in series. Now over here in the middle portion, I3 must be equal to I4, and I will just denote it by I34, and that is the same current that passes through each of these R3 and R4 resistors because they are after all connected in series. The same case happens with I5 and I6. They must be the same current, or they must have the same magnitude of current, because if you notice, the only given is 2 amperes here. That means to say, since R5 and R6 are actually connected in this section of the conductor in series, they must also have the same current passing through each of them. So this is one of the things that should be very clear to you to answer this problem. Now I'm going to simplify this further. I'm just simply going to call I12 to be the current that passes through resistor 1 and resistor 2. And I know that it's 1 ampere because it's connected in series, as I've said. And I will just call I34 the current that passes through resistor 3 and resistor 4. And also the same for I56, the current that passes through resistor 5 and resistor 6. So once you have this very clear in your mind, then the application of the Kirchhoff's rule will be just very easy. And let's start. By the way, I'm hoping you do realize that in this we have two junctions, junction A and junction B, and there is no other junction in the circuit. So let's first start with using Kirchhoff's junction rule on junction A. So for reference, this is your junction A. Notice that I could write this equation, the current I12 plus I34 is just equal to I5. What that means simply is that if I take into account I12, which enters my junction A, and another current I34 also enters through junction A, what goes out is your current 5I5 over here. So I'm going to rewrite this equation to solve for I34. So I get I34 is simply I5 minus I12. And I know each of the values of I5 and I12. I could simply substitute it in the equation. So I get that the current through resistor 3 and 4, or I34, is also 1 amperes. If you think about it, It's just like saying I12 has 1 ampere going in, I34 has also 1 ampere going in. That is why what goes out in I5 is 2 ampere. This is just the sum of the two currents. And that is basically the gist of Kirchhoff's junction rule. The sum of the current is just 0. What goes in is equal to what goes out. Alright, now we are done with I34. We will use the loop rule. Notice that we have two loops in this case, excluding the large loop. This is the first loop. And again, you have the freedom to choose whatever loop direction you choose. And this is the another loop. Okay, so we're going to use the sign conventions here. If we're traveling, meaning the travel means the direction of your loop is from negative to positive of an electromotive force, then that corresponds to plus E. Otherwise, that would be negative E. Now for resistors, if your travel, meaning the direction of your loop, in this case the counterclockwise loop, is approaching or is it's sa Bisaya ani magtagbo gani siya if it approaches the direction of the current. That means to say you get plus IR. Otherwise, or if it moves in the same direction with the current, the loop moves with the same direction of the current, you get negative IR. So we're going to apply that to our first loop. And we get this equation. I'm going to explain each. So I have plus 20 volts. I often like to start with my electromotive force, so that's plus 20. If you notice, I get plus 20 because of the fact that I'm moving, my loop direction is counterclockwise. I move from the negative end of the EMF to the positive, and according to our sign convention, that is a positive value. So I get 20 volts. Now, moving forward, I am now in this section of my circuit, and notice my direction of the current is actually towards the left, and also the direction of the loop is counterclockwise, moving towards the left. And according to our sign convention, when the current and the direction of the loop are on the same direction, you get negative IR. So in this case, negative I1 R1. And I will proceed further with the loop. I'm now here at the third resistor. Notice that the direction of the current is towards the left and my loop is towards the right. So basically, I'm getting opposite direction of the current. The current is going here and the loop is going here. So that means I will get plus I3R3. Continuing with the next resistor, R4, the same case. The current is moving towards the left. The loop as a counterclockwise moves towards the right. So according to the sign convention, you get plus IR. In this case, plus I4R4. Now, moving forward, I get this another source of EMF, E sub 1. Notice that I'm moving from positive terminal to negative terminal. And according to the sign convention, when that happens, you get negative of the EMF. So negative E sub 1. And then moving forward, I'm going up now in my loop, I get negative I2R2. If you notice, the direction of the current and the loop are on the same direction, so I get negative according to the sign convention. So basically, that's just it. You're just taking into account all the voltages across the loop, but make sure to follow the sign convention very religiously. Alright, so out from here, you will get, as I've said earlier, I1 and I2 has the same value, so I simply call them I12, and I can group them, I12. So I'm going to take R1 plus R2, so that's why I have it here. I factored out I12. I also mentioned earlier that I3 and I4 has the same value of current, so I could just call them I34, so that I can factor out I34 here, and I will just have I34 bracket R3 plus R4 minus the epsilon sub 1 or my EMF 1. So when you're trying to substitute all the known values in this case, you end up with this expression. This is simply a matter of substitution of the values of each resistors and equivalent currents. So you can do that simply by substituting, and then further simplifying, you get 20 volts minus 7 volts So this one will become 7 volts or negative 7 volts. This one will become 5 volts minus epsilon 1. So further simplifying, you get 18 volts minus epsilon 1 is equal to 0, which further results to epsilon 1 or EMF 1 to be just 18 volts. So we are actually have solved already the EMF 1. Now, to solve for EMF2, which is located on the loop 2, I think it will not come as a surprise that we are going to use the second loop. And the loop rule is simply taking into account the sum of all the voltages. And let's do that in a short while. Let's first start with E sub 1, E4, E3, and then R5, and then I will go to R2 and R6. Now I'm going to tell you why I did that. So over here, if you notice, you have E1. Notice that E1 here, as I flashed earlier, you're moving from the direction of your travel or loop, moves from the negative terminal to the positive terminal. And according to our sign convention, that is a plus, a positive EMF. So I get plus E1. Now, on the second one, I'm now in R4. My loop is counterclockwise still. So if you notice, the direction of the current and the direction of the loop are on the same direction. So that's why I get negative. So for R3, the same reasoning. The current there is towards the left. My loop direction is counterclockwise. So in this case, it's also moving towards the left. So I get negative I3R3 per the sign convention. Further going down, I'm now in R5 over here. So if you notice, the direction of the current is towards the right. The loop in this case is towards the right also, so you get negative in that case. For I2, I'm now in I2 section. I'm moving from the positive terminal to the negative terminal, and that implies, according to the sign convention, a negative sign of your EMF. So I get negative E sub 2. Now, moving forward in my loop, I'm now in resistor 6. Notice that the direction of the travel of the loop and the direction of the current are on the same direction, so I should get negative of that. Negative I6R6. Alright, so the same with what I did earlier. I understand that I3 and I4 has the same current through it, as well as I5 and I6. So I could simply factor that out so that I would just get epsilon 1 minus I34 and factor out I34, and then that will be R4 plus R3 from here and from here, and then minus I56, and the current is the same since they're connected in series. I could factor out I56 so that I will just have I56 multiplied by I5 from here and R6 from here. And of course, you have minus epsilon 2, which is what we are looking for. Now, it is simply a matter of substitution of the known values and remembering that ampere times ohm will result to volts. So you get this one, epsilon 1. This term here will simply result to negative 5 volts. This third term will result to negative 6 volts minus epsilon 2. And further simplifying, you get, and by the way, you already substitute the value of epsilon 1, which you solved earlier. So epsilon 1, whatever the value we solved earlier, minus 5 volts, minus 6 volts, you get 7 volts positive, minus epsilon 2. And further simplifying that out, you get epsilon 2 or the EMF2 to be simply 7 volts. So that is how you use your Kirchhoff's junction rule and loop rule in solving circuits in network.